So I want you to work out one last problem uh, on zTransforms, and that is the car loan problem. Car loan problem. Is there anybody who has taken a car loan or housing loan or any loan from a bank? Please raise your hands. Those who have got a loan from a bank. Only one person? No, this can't be true. Huh? This one? Okay, okay. So this is what you might have undergone. You may have, you didn't have any idea about zTransforms, right, or whatever, right? Um, so, but this will strike you, right, when you learn the zTransforms and how it get into this column problem thing, right? And for everybody else, for that matter, also. Most of this mathematics in discrete times, right? Part of our life eventually, right? If you monitor anything that that you access periodically, right? And in between these access moments, you have no idea what's happening, right? Uh, so you are dealing with discrete time, and therefore, if you want to analyze the process, you need some mathematics, mathematical tools rather, and that is zTransforms. Okay, now let's go by intuition, right? And see what the problem is. When you receive a loan from a bank, right, you pay it every month, okay, constant amount. You don't pay different amounts, different months, right? It is a constant amount every month. And after a certain period of time, 12 months, 24, whatever it is, right, you are done. You have already paid at the end of the term the total amount, which is the loan plus the interest, okay? So you can write down a simple equation for that part, right? So you can draw it if you want, right? This is the timeline, time zero, right? You receive the loan and you pay back the monthly amount, little amount, right? And after a month, you pay that installment of that month, right? And you keep going. In fact, this U is the what you pay, and P is what you retain with you. Okay, let's say you retain with you P0, the total amount. Initially, this is the loan. Okay, and now after 1 month, you don't owe that total amount because you pay a quantity. You pay a little amount, so you owe less now after 1 month. After 2 months, you owe even a smaller amount because now you have paid 2 installments like that. You are paying gradually, and what you owe is declining, and at some point it goes to zero, right? After the term, Pn is equal to zero. So Pn is what you owe, what you have to pay back to the bank, and it goes to zero. Okay, this is the last installment. Everything is settled. So if you write down a mathematical equation, forget about zTransform or anything, right? Just go by the hunch, right? Um, at any moment of time after k months, let's say k over here, right? What you owe to the bank is p k plus 1. And this is the amount owed to the bank or at the end of the period of 1 month. So kth month, let's say this is the month, kth month. At the end of the month, you owe this amount, right? And if you look at the amount you owe before that month, right? At the start of the month, at the end of the month, okay? That's how it works. Pk is beginning of the month, k plus 1 is end of the month. So if you know how to do that, you can bring it back and forth and fix it, right, to any k. So how do you deal with it? This is the amount you have to pay back at the beginning of the month. And once the month is elapsed, You have kept this money with you for one whole month. So therefore, you have to pay the interest for that. Interest is R. So multiply PK with 1 plus R. Obviously, that's how you calculate, right? The R is actually monthly interest rate, not the annual interest rate, but monthly. So if you receive, say, 100 rupees today at the monthly rate of 10%, at the end of the month, you have to pay 110 rupees, just like that. Okay. So that is this equation. So PK plus 1 is how much you owe, you have to pay back after 1 month, is what you have received before that month, okay, beginning of the month, how much you owe times 1 plus R. But not only that, during that month, you pay some amount, that is you have to deduct that also. So this is how things are connected. So this is very similar to what you have seen in the earlier difference equations. Okay, you had yk plus 1, yk plus 2, yk. How these samples are connected, that is the system dynamics. Now you get some idea of what the dynamics is. Okay, if you didn't have any idea of what the dynamics is, how these samples are related is through the dynamics. And who is telling you the dynamics? Sometimes you're receiving the whole thing as a ready-made dynamic system and the difference equation. Sometimes you have to build it yourself. That is what's called modeling. Through modeling, you figure out how these variables are related to each other, and then you form the model. And the difference equations you have seen earlier are given to you. You have no idea how they were formed. Sometimes they're arbitrarily put together, right? To make a little example. And in this particular case, you know how the dynamics work, and you relate the terms before the month, at the beginning of the month, at the end of the month. You know how interest rates work and what other activities within the month you pay monthly amount. You factor in all these things and fit the equation. So this is basically modeling exercise. Okay, it's not magic, it's not strange, it's pretty much day-to-day thing. Okay, and if you look at a machine, how the things are connected to each other, maybe not very obvious like over here, but that's why you need to write down the equations, right? Kirchhoff's laws, Newton's laws, and then combine them together. Is that clear? Now, because you know how the interest rate works, what you take, what you give back, and all, this is the elementary relationship that will explain the whole process. Okay, right. Now, what we want to do is we want to calculate this U. How much should I pay back every month? Okay, what is that amount for a initial loan? This PK is not the initial loan, but if you set K to 0, it is the initial amount. It is the initial amount that you receive from the bank, the total loan. Okay, but it is depreciating over time as you pay, right? So we want to calculate U for a given P0 and for given R, given interest rate and total amount. We want to calculate U, and also the entire time, whether it is 12 months, 24 months, 18 months, or whatever, right? So what we do is we transform this equation into Z world. That's over here, the Z transform. Each term here, first term on the left hand side and right hand side terms, you have to transform them to Z world. How do you do that? PK plus 1. This is a shift. This is a left shift. Okay, not right shift. This is a left shift. So you have to use the left shift equation for Z transforms and write it over here. And then here, 1 plus R is a constant. PK you transform into Z world, and this is a constant, right? You have to transform that into Z world as well. So this is the definition of zTransforms. Summation from k0 to infinity, the function given to you, and z to the minus k. So that's the definition of zTransforms, right? If you're not very sure how to work out, you can write down the definition and see whether it makes any easier, right, for you to figure out the zTransform. And here is the same, summation 0 to infinity, whatever function given here, and then z to the minus k. Same here. Okay, the function given, which is a constant u, is set to the minus k. Sometimes people forget to do that and just keep it as u. No, you can't do that. It's a constant, the unit function, right? Every month you pay this amount. Right. Then I think to avoid any confusion here, right? You better write this u as un, okay, or change u into a constant, okay, some constant times un. So un is the pulse sequence or sampled unit step, and then in front of that the monthly installment, right? Either you can figure that out. And then this is from the initial value theorem we just concluded before the break. When you shift the sequence to your left, right, by one step, this is the zTransform, right? Is it pz minus is it p0? There you are. P0 is the initial loan, okay? And on the right hand side, it's 1 plus r is a constant times pz. That is the zTransform of pk. And this is u, but sampled unit step, right? So therefore, the zTransform is z over z minus 1. Now see, everything is very clear, right? Very simple. Now you isolate pz on the left-hand side, right? And take the other terms to the right-hand side, and it'll look like this. U z over z minus 1. And this term 1 plus r pz. Pz goes to the left-hand side, connect with this pz over here, right? Eventually you can write it like this. Check all the terms here and make sure whether everything is in order. And then you rearrange the expression on the right hand side into this format. Maybe a bit confusing, but if you look at them, it's unchanged when you go from here to here. Okay, the second term here, u is z over z minus 1, z minus 1 minus r. This whole thing can be broken down into two terms, like here, u over r z over z minus 1 and ur times z over z minus r plus 1. This term and this term combined together, right? So this term and this term combined together is equal to this term, right? Like that. Right. So why we do it like that? Because we want to rearrange these terms so that each term will be aligned with one of the terms in the zTransform table. Okay, because the next step is inverse zTransform. So now if you look at the first term over here, it's a constant times z over z minus 1. So inverse zTransform is pretty easy. This is unit step un, okay, in z world. So we don't have to write un. If you want to write, that's also okay, but we just can keep it like u over r, right? Sort of. And then this one, P0 is initial amount minus u over r. U is the monthly installment over monthly interest rate times, what is this one? Z over Z minus P r plus 1. There you are. So this is a constant raised to the power k, 1 plus r to the power k, right? So then from this equation, you need to figure out you want to get u to the subject on the left hand side and rearrange it as a function of initial loan, right? And the interest rate and also the duration, that is 12 months, 24, whatever. Now, we can clamp the equation for k equals n. Suppose capital N is the number of months, right? So when k is equal to n, right, you don't owe anything back because you had already paid the whole thing, right? So therefore, P capital N is equal to 0. P capital N is equal to 0. Okay. So when you put it there, rearrange, write this equation for k equals capital N, and on the left hand side it's 0, and you can write it like that, right? And then you get u calculated from this equation as like this: r times 1 plus r to the n over 1 plus r to the n minus 1 times p0. So use that equation and substitute to that one any number, say 1 million rupees, right? You get a loan 1 million rupees and you want to pay it back 12 months. Monthly interest rate is 5%, right? Put it there and figure that out. And every time you take a loan, if you go to the bank, you can do your math and go to the bank, and you can figure that out whether the calculation is correct or not. Okay. You can ask what is the interest rate, total amount. You know how to calculate the monthly amount. Any questions, please? Right. So these examples that we worked out today are extremely important, right? So this will make you not shy to write down the expression zTransforms, inverse, and all that, and handle a practical problem in discrete time. Practical problem in discrete time. Okay. Right. If there are no questions, by the way, any questions about zTransforms, discrete systems, difference equations? Before I start the next topic. Okay. Okay, I got some activity in the chat. Everything is clear. Okay, that's good. Right. Our next topic is this pulse response, digital approximations, and stability. I think already you know some of the things when you have the continuous time system and when you deal with it in discrete time, right? There's a time gap between this sample to next, right? And things are not strictly under control, okay? Because we don't do anything within that period of time. We let the system go like freely, Okay. And if we design the system properly, we have some assurance that nothing bad will happen during that period. Okay. So system is stable. Don't have to worry too much about what system is doing between the control points. Okay. Right. But that all depends on how good your approximations are, how good your model is, and how good your controller is. Okay. So a lot of things. Let's first look at transfer function. You have some experience about transfer functions in the first semester in continuous time. I think you know pretty well how to derive the models and how to form the transfer function, how to analyze it for stability and so on. Now this is same thing in a different format, discrete time. So I repeatedly say, because it's very important, in discrete time, we have what is called the difference equations, right? Difference equation. It's all samples. There is no rate of change, no first derivative, second derivative, and so on. They're all samples, input samples, output samples. That's it. And in the middle, you have the system. It's a rational polynomial of Z. This is all what you have, right? So generally speaking, you can write down this equation for any discrete time system. You can see it over here. I think we have seen this earlier also, right? For any discrete system, you can write the relationship between input and output like that. There's a finite number of inputs and finite number of output samples, okay? And they are related through a certain set of coefficients like B0, B1 to Bm, and A1, A2 up to An, right? So this is generally true for any system in discrete time. So these A's and B's, they represent the dynamics in the sense how these variables are related to each other. That's essentially what we call dynamics of a plant, okay? And then when you transform these samples appearing at different times, you can see it over here. This appears at k, this appears at k minus 1, this appears at k minus n. So these are samples at different times, right? And zTransform were developed to combine these samples which are appearing at different times, okay, through the shift theorem. So you can write this down as YZ, this one as YZ, in front of that is at minus 1, and so on. So all these terms can be written in the Z domain with YZ and UZ with respective Z to the minus power, representing the time shift. Okay. So eventually the left-hand side, entire sequence, polynomial in the left-hand side can be written like that with one YZ, and in front of that a polynomial of Z to the minus powers. And on the right-hand side, very similarly, you can write the whole polynomial as UZ, one single term UZ, right? In front of that, this polynomial of Z to the minus 1. And then once you get the ratio between, say, YZ and versus UZ, right? This is very similar to the transfer function in first semester, the continuous time. Now this is the transfer function in discrete time, okay? And on the right-hand side, you get the rational polynomial of Z to the minus powers. The numerator goes to degree m, and the denominator goes to degree n. And for rational partial systems, right, n is greater than or equal to m, okay? So this is true for any system, any discrete system. So remember, Rational polynomial of z to the minus powers is the transfer function in discrete time. Now, if you regard this as the controller, if this is the controller difference equation, where YZ is the control signal and UZ is the error. Let's say, right? This is the block to which error goes in and from which the control signal comes out, and that control signal goes to the plant and excite the plant in a different way, right? So how do we draw the controller structure, right? If you want to implement this controller electronically, you need to draw the structure, how the components are connected and so on, okay? The structure would be like this. You have the error going into the controller, CZ, and what comes out of that is UK. Analogous to continuous time controller, okay? I think this is pretty obvious for you. The error that goes in from the left-hand side, right? And there are a series of Z to the minus 1s, right? You can see it over here, Z to the minus 1, Z to the minus 2, and so on. And every time you go through Z to the minus 1 block, and then you have to multiply with a constant A1, A2, and so on, and then add them together. You multiply, add, multiply, add, multiply, add, and every step there's a Z to the minus 1. Okay. And remember, this Z to the minus 1 is the time shift one step. Okay. In fact, the Z to the minus 1 is a delay, not time advance, but time delay. Okay. All right. So this is pictorially what's happening there. And there are a lot of adders here. When you add all of them together, you generate a total left-hand side signal. Okay. And on the right-hand side, in fact, right-hand side is on the left here, which is the input side, and the left-hand side, which is actually the response or output from the controller, is on the right-hand side here in the structure. So the control signal, which is UZ or UK in time domain, right, is isolated, and you take the other terms, all of the other terms, right, to the right-hand side, and as negative signs. So you add them together pretty much same way you did for the error, and then with a negative sign, right, you combine it with the previous summation and you generate UK. Now, if you want to implement this controller, discrete time controller, so what it takes to do that? Can anybody tell me, what do we need? I mean, what sort of hardware do you need to implement this structure? Let us say, let me horn in a little bit. This is not an analog controller anymore. So therefore, there's no op amps, resistors, caps, and so on, right? It's not analog controller. This is digital controller. When you say digital controller, this is going to be a code, a software running inside the microcontroller or any processing unit. You code it, right? So when you code it, you need to get your error signal. Okay, error signal is coming from outside, right, as a voltage signal, and you want to take that into the microcontroller through one of the digital pins. Okay, or you can connect the analog error signal through analog to digital converter in the microprocessor. You read it. Once you read it, what this is at -1 means a time delay. Now there's a problem. When we draw the diagram, we draw it like that. And sometimes you might misunderstand that this is the error signal which is going through this time delay and appearing here. In fact, within the microcontroller, you have all of these things at once. Error, previous error, previous error, and all that. Right? Exactly the same number of steps that you can see on the right-hand side here. You have to keep those errors in memory. If it is a 5-step thing and operating every 1 second, you need to have the error stored in the register 5 seconds ago, 4 seconds ago, 3 seconds ago, 2 seconds ago, 1 second ago, and now. All these errors should be stored in the microprocessor memory registered. Okay. And when the time ticks by 1 step, you disregard or discard with the most oldest error, maybe at 5 seconds, you drop it and shift all these errors backwards and leaving the space for the new error which is coming up. Okay. Likewise, at all times you maintain the present error and the recent number of errors, right? Error samples, depending on how many is required based on your dynamics. Same is true for control signals. Once you decide your control signal, right, you have to keep it in memory for some time. Because to work out this structure, you need to have UK, which is the control signal, and UK Z minus 1, which means the previous error. And there's another previous error term here, right? All of these terms, as explained by the equation, right? It may be 5, 6, 3, 4, whatever it is. You have to keep those errors in the memory and shift it every time step. Okay. So it's like it's a moving wave like that, right? Error and control signals, right? But if you look at one step, one moment, you combine these error signals, control signals, using these coefficients A's and B's, and calculate your present control signal. Just that. So it is very easy to implement a discrete controller on a microprocessor. Right? It is very easy. There's no hard engineering. There's no need to work with op amps and circuit boards, right? And components like caps and transistors, etc. Okay. Now you have some idea about the discrete signals and how to deal with it. And now we need to look at state space model in discrete time with more details, right? Now, the difference equation you have seen earlier, right, is a generic difference equation. It has present time, that is k, and then k plus 1, or say minus 1, k minus 2, k minus 3, k minus 4, like that. It goes to infinity. Okay, it's a very long chain. Now in control systems, we want to package these dynamic systems into a much more compact and manageable format, right? I can tell you a story in continuous time. If you have a, say, 10th order differential equation in your plant, you write down the equation and you got 10th order ordinary differential equation. That is your model. It's tough to deal with 10th order differential equation, right? So then what we do is we break down the 10th order differential equation into 10 first order equations. Now, even though you have 10 equations versus one equation earlier, these 10 equations are all first order. So it's very easy to implement first order differential equations and solve them, right? Very easily. So therefore, even though we have 10, we don't mind. It's easy. So similarly here, if you have to deal with so many error signals, error now and error a step ago, 2 steps ago, 3 steps ago, right? That is the raw dynamics, right? How the errors and control signals are connected together in terms of the controller, right? It's very, very raw dynamics. But if we can format it into a new mathematical model, we call it state space model. We are going to learn what it is now. Then you can actually pack the dynamics into a different format, much more compact, and also it will be more analytical than in the raw format. Okay, it's all about packaging, restructuring the dynamics into a more efficient mathematical structure. Okay, right. Now, let me get this example so that you can understand what we're trying to do here, right? So we have a plan, y z over u z, and explained by this transfer function, 2 over 1 plus 2 z minus 1 plus 3 z minus 2, right? So when we cross multiply the system, you can write this equation, y z is equal to when you cross multiply, right, this is 2 times u z comes over here, and then y z you can isolate on the left hand side, and all the other terms 2 z to the minus 1 y z and 3 z to the minus 2 y z. These two terms, right, after cross multiplication comes back to the right hand side, right? And once you have written it like that, you can assign new variables to previous samples of the signals, right? For example, if you look at the oldest sample here, say if you start with the y, right? Y z in front of that z to the minus 2 means this is yk minus 2. Okay, and this is y z in front of that z to the minus 1. This is yk minus 1. Okay, and y z in time domain is yk. Okay, so this is entirely the time domain dynamics, and this is the difference equation of the plan. Okay, right. So this is the oldest sample, yk minus 2. This is more recent, yk minus 1. And this is now the present sample. So if we stick to a particular convention, like what I have written here, go to the older sample, and you can see that this is k minus 2, and figure that out. Two steps. Okay, and assign a new variable using, say, x, for example, right? X subscript 2, right? X sub 2, and don't write time k minus 2, but write just k. There's no minus 2, minus 1, minus 5, nothing, right? The new variable has timestamp k, present time, and it is tagged to yk minus 2. And the moment we see x sub 2, we know that this is yk minus 2. We know that, right? They are related. This is assigning a new variable in the present time to which is equal to the other variable y 2 time steps ago. Okay, you are assigning the new variable which is equal to the y variable 2 time steps away, okay, ago. And if you look at the other one, more recent sample, k minus 1, which is 1 step ago, right? And look at this 1 here, 1 step. So you write down x1, another state variable, another variable different to x2. This is x1, okay? and time is k, present time. All right. So you have to do this, right, repeatedly, as there are uh, uh, old time samples of yk. Okay. And if you look at the left hand side, yk, do not write another state variable for that. Okay. Because it is already in the time domain, it's present time k, right? But what you do is that if you look at this one, yk minus 1, okay, the same sample, right, this yk plus k minus 1, now as x1 k, right? If you step up this k to k plus 1, this yk minus 1 would step up to yk. You know that, right? You know that. So this is like you have a set of places to store data, and you keep storing data from yk minus 2 goes into x2 box, and k minus 1 goes to x1 box. Okay. And when the time advances, what you do is that, right, in k plus 1, what you do is you take this value and swap it with the present value, the next value. Okay. Every time, say, you change the values. Okay. You remove the value and move it to the other variable. Say, for example, x2 box, whatever you had x2 box, right, goes to x1 box after one time step. Okay. So this is a little technique that we do to bring all the past information into present context, past information into present time. And if your denominator is a second order, you assign two state variables, x2 and x1. Okay. And when you do that, you have the dynamic equation, the difference equation over here with yk on the left hand side, and this one is the first state variable, right, x1k, and stepping up by one shift. So x1 k plus 1 is over here. Okay. And similarly, if you look at this one, x2k, right, after one time step, what will happen that this value will come over here, right? So x1, what will x1 contain would be the same value that was there, right, at time k. Can you see that? So x2k plus 1 is equal to x1k, and x1k plus 1 is equal to x0k, but we don't assign any 0k here, right? We do the assignment starting from the oldest one and work it out to the left hand side, but when it comes across the equal sign, we don't continue any further. We don't continue any further. So now we have two state variables, x2 and x1 at time k, and also x2 and x1 at time k plus 1. Can you see that? You want to get to this format. See here, this one and this one. This is x1 and x2 at k plus 1. What is this? This is x1 and x2 at time k. So it's very elegant. Remember the format, right? So you convert the difference equation to this format. Forget about the control signal, right? Look at the response, right? Present time, one step ago, 2 steps ago, 3 steps ago, like that. You write it like that and keep assigning state variables starting from the oldest one. Here it is 2, so x2, x1. And then right below that, write down, say just below x1, you write x2 k plus 1. And on the left hand side, it is x1 k plus 1. Okay. There's no need to assign x3 because this is a second order plant. You have only 2 time steps, k minus 1 and k minus 2. And if you look at these two equations over here, you will see that you can write down this equation x1k is equal to x2k plus 1. Okay, so that is what is called the state equation. And x1, okay, let us write it here, and you can see it over here, the state variables. After writing the state variables, you can write the state equation. You can see it over here, right? 2 state equations. If you look at the second state equation over here, oops, this one, right, which is very obvious over here, x2 k plus 1 is equal to x1 k, right? This is the way we have assigned state variables in the first place, but it is a state equation. The other one is the system dynamics over here, right? The system has certain connections between the state variables, right? So that is already explained here. This is x1k, this is x2k, this is x1k plus 1. So you write down x1k plus 1, all right, is equal to minus 2 times x1k minus 3 times x2k plus there's a control signal uk, right? Now see this nice pattern over here. On the left hand side, you have the 2 state variables x1 and x2 at time k plus 1. Let's call it next moment, next step. And on the right hand side, you have these 2 expressions that you can rearrange into a matrix representation like this: minus 2, minus 3, 1, 0 as a matrix. And after that, x1k, x2k. So when you multiply first row column, you get the first equation. Second row column, you get the second equation. Okay. Plus 2 times uk. uk goes into the first equation only, so it doesn't go to second equation. So there's a 0 here, right? And what is our output of the plant? Output is yk as given by the dynamics. So now we have 2 state variables, x1 and x2, and yk is equal to what? Yk is equal to x1 k plus 1. x1 k plus 1, right? This yk is x1 k plus 1. So this is what is called the state space model of the plant. So what I expect you to learn from here is that if you are given the transfer function as a rational polynomial of z to the minus powers, preferably, can you break it down into state equations, state variables, and then form the state equations, and then find out the state space model of the plant, right? So that is absolutely necessary if you want to deal with discrete time systems. Any questions, please? Is everything clear to everyone? Ramesh, is that clear to you?
Yes, sir.
Vihangi?
Yes, sir.
Okay, Dayavans?
This is clear.
All right. Chaturanga? Is it clear? Is everything clear? Vijay Tilaka?
Yes, sir.
Jokshan AK?
Yes, sir.
All right, good. There's some activity on the chat. The state space model can be only used for discrete system modeling, or can it be used for analog system modeling too? Of course, yes. You can use it for analog systems, continuous time systems, and discrete time systems, both. We will do the state space model for continuous time maybe on another day. They are the state space is slightly different to what you saw here, right? Here, the state variables are the samples at different times, k minus 2, k minus 1, and so on, right? Samples. Because that's what we have in discrete time. We have nothing but the samples, always samples, right? So in continuous time, we don't have samples. We have the function and its derivatives, first derivative, second derivative, third derivative, and so on. So therefore, we assign state variables, say one state variable to yt, right? Yt, simple time, continuous time. And then dy by dt, rate of change of y, and that's another variable. Then d square y over dt square, the second derivative, that's another state variable. Like that, you assign state variables in continuous time using the differentiation. Okay, that's one very common approach. So if you have say a vehicle, so vehicle has the position, has the velocity, has the acceleration, has the snap, the jerk, like that. So you can assign variables y1, y2, y3, y4, x1, x4, x2, x3, like that for the derivatives, successive derivatives, right? And then form the matrix structure very similar to what we have seen here. Okay, right. Okay. So here it's very similar to what we have already covered. You have YZ, right, in Z world, and all the other terms, previous sample at 2 steps back, and all that, right, in time domain. It look like that, and you keep assigning state variables, right? Earlier, it was just a example, right? Like that. Now it's a second order thing, 2 time steps. But in this slide, what I try to do is to generalize it for any time steps, right? So just that. So please look at it. It goes up to n steps, z to the minus n time steps, right? You need to have n samples in your difference equation. So you keep assigning state variables starting with the oldest one, yk minus n. So this is assigned xnk, and work out backwards xn minus 1, xn minus 2, like that. It reduces, and eventually you get the first term on the right hand side, right? x1. So this one has n number of state variables and it's a nth order system. You have n state equations also, right? And after that, you keep writing the state equations, right? The oldest one, xn, right? You write it xn, this one, oldest one, xnk. But what is xnk plus 1 in the next moment? This is xnk. Xnk plus 1 is this one, xn minus 1k. The way you have assigned the variables is like that. So let's say you had 1,000 rupees in your pocket 2 days ago, right? And that is like yk minus n 2 days ago, right? Now, that's as of today. Now, what about tomorrow? Tomorrow is Monday. So when you go to tomorrow, you can say you had 1,000 rupees 3 days ago. So that is just changing the time step, right? From k to k plus 1. So similarly, these state variables are related to time. Is what you had 3 days ago, today is what you will have, right, in your pocket 4 days ago when you look at the same problem tomorrow. Okay, so it's like that. So dynamics is basically how you go from one step to the next step. System dynamics is how, as you saw, how things are related, but what it really does is that it gives you a way to calculate what's going to happen to the plant as you advance in time, continuous or discrete, right? How do we get from k to k plus 1? So if you have the equations written down to explain how you get from k to k plus 1, that is what is called the dynamics. So here what you can see is that these state equations, they tell what's happening to each and every variable, state variable, okay? So xn k plus 1, right? If you want to find out xn k plus 1, just look at xn minus 1 at k. Same thing, same thing, okay? And then when you write down these equations, right, from n minus 1, n minus 2, up to x1, right, you get all of these equations written. The first one at the top here is coming from the system dynamics. This is actually the dynamic equation of the plant, right? How do you calculate x1 k plus 1, right? x1 is very important, right? How do you calculate the first state variable at time k plus 1, right? It's not as simple as this one. This is how you have assigned the state variables, but this is how the system changes, right, from k to k plus 1 with combination of all the other samples present and in the past, right? How the system is connected together. That is described over here, right? So this is what is called the control affine system. When you write it down in this format, you can see these ones all along this one of these lines, and most of the other ones are zeros, except for this one. This has the coefficients coming from the system difference equation. All right. So this is all alternately known as controllable canonical form, right, or control affine form. When you have this format, you can look at this big matrix, right? It's not necessarily big all the time. It depends on how long your difference equation is of the plant, right? How far you go back in time. Depending on that, the size is decided. And looking at the matrix over here, you can tell a lot of things about the plant, right? The system, whether it is observable, whether it is controllable, and all that. A lot of properties of the system can be studied and understood using this one and also this one. This is how the control signal is connected to the system, right? Where I actually provide this energy to which variable, how much and all. So that will tell this is the state space model is very, very useful. This kind of modeling was actually um, relatively recent in 1970s. Um, um, People like Rudolf Kalman started this kind of modeling and then try to analyze the plants through the models, right, using linear algebra, uh, and that opened a new chapter in control systems, uh, known as modern control systems, right? Okay, so in a way, most of the techniques that we studied last semester are actually classical controls, right? Classical controls. But most of the things we are going to do this semester is under the modern control systems. If you look at these ones, you can clearly see the classical part and the modern part. Okay. Um, right. So that's all for the day. Any questions, please? There's a question about fuzzy. Well, yes, as you said, it's out of scope, obviously. But if we have time towards the end, we'll spare a little time to talk about fuzzy. I teach fuzzy for undergrads in final year in autonomous systems. If you really want, I can let you join that module when I teach next time for final years. You can take that class. Yeah. Otherwise, it's mm, conceptually anybody can explain fuzziness and fuzzy controls briefly in half an hour, but you don't get anywhere with that. So it takes a little more than that if you really want to do something with fuzzy systems, right? More than that. So I think best thing is that I can let you join the next semester final years when they do autonomous systems. I don't teach the entire autonomous systems. Dr. Pesha and myself, we teach together. So when I take my part, fuzzy is just part of my part. I'll let you know so that you can join, right? Excellent. Any other questions, please? Right. Then let's wind up the class today. And please do these homeworks at home. I will upload them to the web and videos will be available on YouTube, right? But I couldn't do that yet because I think Windows 11 has taken out this video editor app in the system, and now it is not available. I don't know whether it is a problem in my computer or a system change from the Microsoft side. Other free video editing tools, I'm not very sure about it. They always have get access to my Gmail account, etc. And some are online. These big files you can't edit and upload online takes a lot of time. I want to store in my computer and upload to YouTube in one go. So therefore, it's a bit of problem. I will sort it out and upload all the videos in a day or two, right? The lecture slides will be available maybe tonight on the Moodle. Right. Okay, let's wind up and I'll see you next week. Thank you.